Good evening, everybody. Thank you for joining the Auckland Astronomical Society YouTube channel, and welcome to the September talk for Introduction to Astronomy. Let's get started. This image here is one of my favorite images of all time in astronomy. It's a picture in X-ray wavelengths of Cassiopeia A supernova remnant. And it was taken in 1999 by the Chandra X-ray Observatory. And to me, it's just amazing. You can see all some of the details, all the complex structure around most of the remnant all around here. Look, right in the middle, you can see the central neutron star that's shining bright in the middle there. So to me, that begs the question, how and when did X-ray astronomy get started? And that's why tonight's talk is titled Cosmic X-ray Astronomy. And in the talk, I intend to identify the two crucial early decades, the 1960s and the 1970s, when it all got underway and started to snowball. We'll identify the early pioneers in this field of astronomy, the missions that they oversaw, the discoveries that they made that really set the platform for further developments and more sophisticated instruments and observatories to show the exact image you see now. So I'll do this by breaking the discussion into 6 chapters. The first one will be Introduction to X-ray Astronomy in general. Chapter 2 and 3 will cover the 1960s, early X-ray astronomy, in the 1970s, X-ray satellites. And you'll see the asterisks there. And that's because I want to highlight this is where my focus of my talk is going to be, on the 1960s and the 1970s. We'll then briefly go over the 1980s, some of the continued advancements. We'll briefly go over the 1990s. A lot happened in there, but in particular, I want to mention 2 advanced X-ray telescopes that were launched in the 1990s that are still going strong today and producing good astronomy science. And then last chapter, chapter 6, we'll have a summary of what we've covered, and we'll give you some homework, some bit of exercises to do, which is always fun. So chapter 1, Introduction to X-ray Astronomy. Thought we'll discover about we'll talk about the discovery of X-rays, who and when and how, the properties of X-rays in general, and the importance of X-ray astronomy. So it was in 1895, a German physicist by the name of Wilhelm Röntgen, and he set himself up here a metal vacuum tube, and he started experimenting around and sort of ran some really high energy electric currents through this vacuum tube. And he found what happened, what emanated from that vacuum tube was these really high energy invisible rays, in which he called them X-rays because they were invisible. And what he did find out by accident, that these rays actually penetrated human tissue. Just to show you, put your hand in front, and he did that with his wife and one of his colleagues. And of course, we all recognize that as looking like an early day X-ray, and indeed it is. So from there, of course, X-rays have many applications in science, everyday life, and here's your classic one you think of, a basic chest X-ray getting done in medicine. So how are the properties of X-rays? Where do they sit in the electromagnetic radiation, the full spectrum? Well, here in the middle, as you know, is you've got visible light, and that's got wavelengths of about roughly 400 to a little over 700 nanometers. And down at the low energy spectrum, you've got your radio waves down here and your infrared. And higher up, you've got your ultraviolet, X-rays and gamma rays. So the X-rays sit in here, high energy, very short wavelengths from 0.03 to 3 nanometers in comparison to, say, 400 to 700 for visible light. The energies of the photons are then split up into soft X-rays and hard X-rays. The soft X-rays are those between 0.5 and 5 kilo electron volts. Electron volt is the kinetic energy an electron would gain after being given 1 volt of energy. And then you've got the soft ones, and the hard ones are 5 to 30 and higher a kilo electron volts, and they're called hard X-rays. Now, interesting enough, X-rays get absorbed by the atmosphere, the higher layers called the ionosphere, where they ionize the molecules up there, and in the process they get absorbed and can't penetrate any further. So the lower energy soft X-rays, they penetrate down to an altitude of probably about 150 to 200 kilometers, so they don't get too far into the atmosphere before they peter out and can't penetrate any further. So in other words, you've got to get up to at least 150 to 200 kilometers in the atmosphere to be able to see these soft X-rays. The hard X-rays are higher energetic, so they can penetrate down to an altitude of about 40 kilometers in the atmosphere. So you immediately see from here, the logic is really X-ray astronomy never really took off until the age of rockets, the space age. The importance of X-ray astronomy, what they do, these X-rays that come from space, they reflect high energy process and events that are happening outside of Earth. And you tend to split them into two groups. One is the solar system, and the two main causes of X-ray emission in the solar system are from solar flares from the sun. In fact, that's how you classify solar flares, is by the nature of the X-ray emission. And orbital, also at Jupiter's polar regions, where you get charged particles from the sun getting trapped by the magnetic field, getting directed towards their poles. And just like we get an aurora on Earth at the northern and southern poles, you do at Jupiter's poles as well. Beyond the solar system, that's what they call cosmic X-rays. And it's multiple sources and processes can be responsible for this. And I've just put the main groups here for you. First of all, thermal X-ray radiation. Thermal radiation refers to emission of light that reflects the temperature of something, particularly the surface temperature. And a classical example is neutron stars. Their temperatures get up to 1,000,000 degrees Kelvin quite happily, and the X-ray emission that they emit reflects that high surface temperature. There's another type of radiation that emits X-rays, and that's called Brennstrahling radiation. And here's typically you get this in the hot gases within galaxy clusters, so the intergalactic medium gases. The temperatures there get up to about 10 million degrees. And what happens here in this diagram I've got here, you've got a high velocity electron coming in, it interacts with an atom of some gas, and as it interacts with the nucleus, it gets deflected off, and in the process slows down and gives out X-ray radiation, or photons, as it gets deflected and loses energy. And if you analyze Brennstrahling radiation from there, you can get an idea of the temperature, in other words, the kinetic energy of the gases, and also the composition, what sort of elements you've got in those gases. Two other forms of X-ray radiation that's important in astronomy: synchrotron radiation. That's where you get magnetic field lines with high energetic charged particles, usually electrons. They're spiraling around magnetic fields, and as they spiral round and round and round, they're essentially accelerating. So they give out radiation, and it's a particular type of radiation that you can identify. You can do an energy spectrum diagrams and clearly see it fits the picture of what they call synchrotron radiation. That radiation often has a degree of polarization in line with the magnetic field lines, and that's another clue that what you're looking at there is synchrotron radiation. And if you see that, you know you've got an environment where you've got high-speed charged particles going round and round magnetic field lines. The other process that can do astronomy-related X-ray radiation is called inverse Compton scattering. That's where you get relativistic, which means traveling close to the speed of light, charged particles, travels through, and it strikes a low energy photon. So you've already got a low energy photon, you get a high energy particle striking it, imparting that energy and bumping it up, whereby that photon becomes an X-ray. And a classical example is where you've got the cosmic microwave background photons that are in the microwave, so low energetic. You get cosmic ray electrons. Cosmic rays most likely come from supernova explosions. They get pretty high velocities. They go along, they strike a cosmic microwave photon and impart that energize, and it turns into an X-ray photon. So those are your main forms of astronomical causes and processes that cause X-rays that are worth looking into. So chapter 2, yeah, here things start getting interesting. The 1960s, early X-ray astronomy, in particular cosmic X-ray astronomy. So we're going to talk about counter Geigers, or rather Geiger counters and proportional counters. They're the detectors that they first started using to detect these X-rays. We'll talk about the initial sounding rockets and balloons. And then we're going to introduce you to three very important giants in the field of X-ray astronomy. So Geiger counters were the first detectors or instruments to detect X-rays, because you normally, if you try and get an X-ray, it's so high powered, you try and strike that into a mirror, or most detectors, it just goes straight through. So you've got to detect it indirectly. And what the Geiger counter essentially is, you get a sealed metal tube with a vacuum in there with some gas, and in that gas, you get a window along here which acts as a filter. And it allows only a specific range, whatever range you decide to pick on, a particular range of X-ray photons, energy ranges can come through that window and come on and interact and ionize the gas that's in there. Often it's argon or xenon, and it ionizes it so that it gives off electrons. The electrons are then attracted to an anode, which is a central wire electrode that's positively charged. The electrons join onto that, and then that completes an electrical current, which goes up here, and you can then measure the strength of that electric current, and that reflects the number of X-ray photons within that energy range that you're interested in. And hence the name Geiger counters. It counts the photons. There's a problem with that, of course, that sometimes it's not easy to differentiate between, hey, well, if you're allowing quite a wide range of energy X-ray photons in there, it won't tell you how many are in this particular energy levels and below it, and so on and so on. So then they came up with another development. They created what they call proportional counters, whereby they're able to amplify the energy pulses that came from this process of ionization, whereby the amplification was proportional to the photons of different energy levels. So in other words, if you had more photons of a particular energy level than another particular range, and both were coming through your filter, your instruments would tell you that in proportion you've got more of this higher levels. So that's how they measure X-ray photons. So the first guy really to get involved with X-ray astronomy was a guy called Herbert Friedman. And he, from 1949 through to the early 60s, with funding from the US Naval Research Laboratory, managed to get himself some captured V2 rockets, German rockets from World War II. And they put their Geiger counters on these rockets, the V2 rockets, sent them up to altitudes of about 150 kilometers. The Geiger counters, to give you an idea of their size, was about 1 square centimeter, so about yay big. Couldn't detect, sort of not large by today's standards, but was sufficient to start detecting X-rays. They did detect X-rays up at 150 kilometers. They were from the sun. They analyzed them and decided they were from the sun. They also thought, well, gosh, these X-rays that are coming from the sun, they're pretty weak. And they estimated they actually only represented 1/1,000,000th of the total energy output of the sun. They thought, well, if the sun is only putting out, and it's so close, and we're only detected so many X-rays, the only reason we're detecting them is because we're so close to the sun. So really, certainly with today's their of the day technology, there was just no point in looking for cosmic X-rays. It was just a pointless task. Our nearest sun, the star, is so close, and even then we just get a weak signal for it. So that was pretty much the end of cosmic X-rays. It was put to bed. Don't worry about it, guys. And Herbert Friedman got on and did a lot of study involving the ionosphere and X-ray emission from the sun, and it all did very well. Now, so from there, along came another couple of characters, and in particular, Bruno Rossi. He was an American-Italian experimental physicist. And he had the insight to start thinking about it. He was driving home from a meeting one night. It suddenly dawned upon him that soft X-rays from right across the galaxy could quite happily travel the distance across the galaxy unimpeded. No one would believe him. No one took any notice of him, but he came up with that insight. He was working at the time at a place called American Science and Engineering, which is a private company developing new technology and science detectors and so on. It was actually at one of their social functions. He bailed up a young 28-year-old Riccardo Giacconi, another American-Italian guy. And he said, look, you know, you're only 28, you're wanting to get ahead with your career, and I see your forte is developing new detectors and technology and so on. Would you like to team up with me? Because I think if we get above the atmosphere, we start looking for it with new technology. I reckon that the soft X-rays out there will be detectable, contrary to the general astronomical community's opinion. So they did. The two of them got together. They had funding difficulties. NASA didn't want to know about it. Admittedly, NASA was only 2 or 3 years old at that stage, but interesting enough, NASA just looked at the proposal and said, no, there's no merit in there. So what they did was quite cunning and clever. They said they went to the Lunar and Planetary Exploration of the Air Force Cambridge Research Laboratory in the US. And they said, look, we're speculating that X-rays from the sun that can reflect off the moon. Furthermore, those high energetic photons may interact with some particles on the lunar surface, which in turn may emit X-rays. Wouldn't it be neat if we put up a rocket and with a detector on it and studied the moon for X-rays? Joe, it's lunar and planetary exploration. So yes, they were granted the funding to do that. So what they did, the funding enabled them to get 4 two-stage Aerobee 150 rockets, and that could take them up to an altitude of 225 kilometers. They got themselves, instead of one by one square centimeter Geiger counter, they got themselves 3 Geiger counters that were 10 by 10 centimeters, so 100 times more sensitive. The field of view was 120 degrees, so nice wide field of view compared with the previous 3 degrees by Herbert Friedman. So they sent their flight up there, and suddenly they thought, oh, we're up looking at the moon. Oh, goodness me, we now have the instruments to do a full flight scan off the sky. So they did. And these, of course, were night missions because they were no longer studying the sun. So they waited to full moon, launched their rockets to look at the moon. And while they were up there, they swung their equipment around and had a very good scan of the entire sky. Now, most people just either didn't know about what they actually were up to or certainly thought they were going crazy. But their results shocked the world of astronomy, blew everyone apart. So this first mission was on the 18th of June, 1962. And here is their data from the original paper. And you'll see there's 2 striking things here. First, look at all this. Here's 0, no X-ray counts, which the astronomy world thought they would get if they did that. But look, there's a constant background right across the entire sky, a diffuse background of X-ray emission. And look at this, a huge big peak, and that was coming from the constellation Scorpius. So it was labeled Scorpius X1, the first X-ray source to be identified. And look how strong that signal was there up here. So there was those 2 main findings just blew everyone apart. Oh my gosh, there's X-rays abundant in the sky to be seen. We better go up there and have a closer look. And that's what did. Further missions came from there. There was, they were all what they call sounding rockets at the stage. They just go up for a few minutes, get above high into the atmosphere and come back down again. In October 62, a flight found another localized weak source of X-ray emission. They thought that was about 2 degrees to one side of the Crab Nebula. That's a known supernova remnant. Another flight in July 1964 had a closer look at that, and they said, whoa, guys, that's a whole entire light year across. So suddenly they were realizing there are numerous sources out there, starting to identify them. They're saying, look, just this one source is an entire light year across. a balloon flight in 1965 that was looking at hard X-ray emissions from 15 to 60 kilo electron volt energies. That confirmed, got a better look at it and confirmed it. Yes, guys, that is coming from the Crab Nebula. Most of you know that is M1, Messier object number 1, which is in the constellation Taurus in the summertime. And it's just a very faint thing you can see with a good telescope. You might say, well, what are they doing with balloons? And they've got, you know, when you've got these rockets now. The thing about balloons, the rockets had the advantage they can get up really, really high, up to 200 kilometers up or so, and that they could get a good, decent look at the soft X-rays. But the balloon had the advantage it can go up for many hours at a time. And as we said, the harder X-rays come down to lower altitude. So the balloon couldn't get as high as a rocket, but it could get high enough to have a good look at those hard energy X-rays, and it could stay up there for much longer, you know, up to 100 hours versus just a few minutes of a high altitude sounding rocket. So you can see they both had their place. And the 1960s was pretty much dominated by sounding rockets and balloons. So further missions went on, and you can see here they identified much other further sources in the galactic plane here. See all these little spikes. Here's your diffuse X-ray background, and there's little spikes up here. Here's your Scorpius X1 that Riccardo Giacconi first identified. See how powerful that was? But you can see there's numerous other sources there. They realized there are quite a few sources of X-ray emission going on in the galactic plane that these primitive instruments of their time could detect. They also detected, they confirmed the Scorpius X1, there it is here, and they discovered another one called Cygnus X1, which we'll talk about later on in the talk, which is really, really interesting. So we'll go on to talk about that shortly. So what you might say, well, what was the Scorpius X1 source that they picked up? Was that so strong in the sky? What could that be? Well, they analyzed it and they concluded this was the first indirect observational evidence that neutron stars existed. And you probably remember neutron stars, a common one of those is pulses, that pulse radio signals that were discovered in 1968 by Jocelyn Bell and her supervisor. Well, here these guys were in the early to mid 60s. They identified Scorpius X1. It was a Russian astrophysicist who looked and analyzed the X-ray emissions and the optical counterpart. In other words, what can you see there with a normal telescope? What's going on where we can see these X-rays coming from? And it was as early as 1967. They analyzed that data and they said, hey, this fits the picture of a small, dense object that's accreting material from a binary red giant. In theory, they knew the stuff could go on. So what you get here is probably from my previous talks, you get a big, massive red giant right next door to these compact little neutron stars, which have the mass greater than the mass of our sun, squashed into something that's about 20 kilometers across. So very small, dense, compact objects. They siphon the outer material off the red dwarf, off the red giant rather, form these accretion disks of hot material that spirals around and it drops onto the surface of the compact, dense neutron star, and X-rays get emitted. So they knew in theory that those sort of objects may well exist. And because they analyzed the X-ray emission they picked up, they put it together and they said, this almost certainly is what we're looking at. So they actually picked up the evidence of a neutron star before they were actually seen more directly by Jocelyn Bell with her radio pulses. So chapter 3, so there's 6. So that's the 1960s, those 3 key guys. They had the insight to go looking for X-rays. It was dominated by sounding rockets and balloons. And they said, yep, to our surprise, there's just a diffuse X-ray background with some nice big peaks in here. And they found evidence for neutron stars. So the 1970s was pretty much dominated by satellites. There was 5 key X-ray satellites that were launched in the 70s. These are them here, which we'll go over now. And of course, a satellite means you're not going up and down like a sounding rocket. You're going up there in Earth orbit and you're staying up there for as long as you've got fuel and energy to keep going around, which is usually a few years. They keep producing data. So the first one here was officially known as the Small Astronomical Satellite, the SAS-1. NASA actually had a few SAS satellite projects on the go, and there was 2 of them dedicated to X-ray emissions, SAS-1 and 3. Now, SAS-1 was also known as Uhuru. The reason behind that, they launched it from Kenya in December 1970. Of course, Kenya had a nice equatorial latitude, and you get that assistance to get a higher payload into Earth orbit. And they launched it on December the 12th, I think it was, 1970, which was Kenya's Independence Day. And Uhuru in Kenyan language means freedom. So here you've got this is it here in some pre-flight tests. Here is Bruno Rossi himself doing some checks. This lady here is Margaret Townsend, and she was the project manager for all of the NASA's SAS satellite program. So that was a very first for them too, the first woman to have such a high sort of technical position within NASA. So this is what it looks like here. You've got some solar panels, you've got a star sensor and sun sensor. That's to allow it to works out where it's pointing and so on. So it gets a sort of rough idea of the location of these sources. Instead of having 1 and then 10 by 10 square centimeters, look at these guys. These guys have got proportional counters now. So in other words, you can start to differentiating the numbers of photons and the X-ray wavelengths at different energy levels versus just getting one big figure. And they had 2 840 square centimeter proportional counters. So you can see that those are huge compared with the previous ones. The fact that they were in orbit the whole time allowed them to do prolonged observing times, which was ideal for faint and extended or complex objects. The 1960s could just go up there and say, yeah, we're seeing a source roughly over here, roughly over here. These guys could go up and identify much fainter things, get a much better grip of exactly where they were and the extent at which they went. So over 2 years, Uhuru worked for a little over 2 years. It did a total near-sky survey. It identified 339 X-ray sources. Not only identified them, but was able to say within reason their location in the sky, how intense they were, and their variability. Variability, interesting enough, a lot of X-ray sources are variable in their peaks of X-ray emission, which we'll find out shortly. Well, you met the one of them already, the neutron binary star system. So you can see immediately you've got another generation of technology. And also, who do you see here? You'll find out tonight as I go through that these 3 guys right along through the 60s and 70s, they were the big names behind all the technology over these sort of crucial decades. So, some notable observations. Centaurus X3, in other words, in the constellation Centaurus, they noticed an interesting sort of object of variable X-ray emission. X3 means it was the 3rd X-ray emitting source in that constellation. And this is what the light sort of curve and X-ray wavelength looks like. And it was sort of regular, sort of little over 2-day fluctuations, short pulsations, just over 4 seconds. And what they worked out was when they analysed it, what were they looking at? You might think what they were looking at was an X-ray pulsar with an occultic binary system. Okay, so what's an X-ray pulsar? You've probably heard of the general pulses that in radio wavelengths that they emit radio waves and they rotate around and round, and that they do a bit of a like a lighthouse sweeping around. Well, neutron stars can do the same also if they're in a binary system with another red with a red giant in a binary system, and they start siphoning off that material like you saw on the previous example. But instead of the material just haphazardly and from the accretion disk falling on to the neutron star at random, what's going on here is you've got a neutron star that's highly magnetizing, that's rotating very, very quickly. The infalling material is charged particles, usually hydrogen. It gets directed by the strong magnetic field lines and gets dumped and right onto the polar regions of this rapidly rotating, highly magnetized neutron star. So the X-ray emissions, or the hot spots, are at the poles and get shot out that way. So instead of a radio pulsar wobbling around and just emitting radio waves, this time you've got X-rays being emitted from this rapidly rotating neutron star. So, and of course, in this binary system, it was occulting. Instead of, you could actually, the red giant was getting in the way of the neutron star emitting X-rays from its poles. It was sweeping around it. And that's exactly what you see here. And that's why you had these nice big dips. So you had these 4.84 second pulsation periods. That was because of the neutron star spinning around, emitting X-rays, high energy X-rays from its poles. But you had this red supergiant right next door to it, which was occulting or blocking the star on a little over 2-day cycle. And that there explained that pattern that they saw. So you could almost, so you could see here very clearly a whole stack of new way of observing different astronomical processes and objects was coming to light through just observing the sky in X-ray wavelengths. Cygnus X1 that I mentioned earlier on, that they detected in the 1960s. They analysed it further here because they could observe something for longer periods and get a better idea of exactly where in the sky it was. So you could look at it, maybe its counterpart in optical wavelengths, but get an idea of the pattern of amplitudes and pulsations and so on. And what they determined was that there was some pretty large amplitude pulsations, real high pulsations, but really, really short duration. And there was no stable period longer for about 10 seconds. And when you're observing any sort of source and it's rapidly changing, very, very rapidly, that tells you that that source is very, very small. And they calculated that the source of this X-ray emission was smaller than the size of the Earth. They then looked at it through with their optical telescopes, and they identified that it did have a partner as part of a binary, close binary system. And in fact, it was a blue supergiant companion. And when you get a binary system of two stars going around one another, if you know the mass of one and you know how quickly they're going around from one another, there are equations you can work out the mass of the second one. And of course, the second one that was emitting X-rays was invisible, but they could work out its mass. The mass calculated turned out to be greater than 10 solar masses in a size smaller than the size of the Earth. That immediately tells you, looking at something that's invisible, that's extremely compact object and powerful. And that was the first observational evidence of a stellar black hole. Einstein's general relativity had predicted black holes. In theory, they existed. There was no real evidence that they'd seen them on an observational basis. And it was X-ray astronomy with Uhuru, the first satellite in the 1970s, that gave the first observational evidence of a stellar black hole. So that was a huge milestone in not only X-ray astronomy, but all of astronomy. Also, the Uhuru paid a lot of attention to galaxy clusters, in particular the Coma, Perseus, and Virgo galaxy clusters. And when they looked at them, they found a lot of hot gas emissions. We talked about the Brenn-Strahlung radiation earlier on. And they determined that this one here's the Coma galaxy, and there was a lot of hot gas dispersed right throughout the entire galaxy cluster. Gas is up to 73 million degrees Kelvin. And to hold sort of such high kinetic energy, high hot gas like that together in a certain space, you need a lot of mass for gravitational influence to keep that contained within the galaxy clusters. But when they added up all the mass in the galaxy, there was insufficient mass from the galaxies to actually account for your ability to hold all that really hot, highly kinetic energy gas zipping around in that. And that was the sort of one of the key factors that strengthened the argument for people saying, hey, there's dark matter out there. There is mass and matter out there in the universe. We just can't see it. It's out there. And this was a really strong argument for that. And here we are, look, in the early 70s with the first X-ray telescope, X-ray satellite rather. The next discovery that Uhuru made was very, very productive. It concluded they did a lot of study of the X-ray emission from Seyfert galaxies. Seyfert galaxies are galaxies that have a very active center. They've got a supermassive black hole in the center of, that's what we call active. Material is being feeding into it, and it's firing out a lot of energy from its poles, active galactic nuclei. And galaxies with active galactic nuclei, AGN, are called Seyfert galaxies. And they concluded by studying them that these Seyfert galaxies actually generate and account for 25% of that diffuse background X-ray emission. Remember, this is Giacconi's data that showed this right across the sky. There's that background of X-ray emission independent of these other little spikes. And they concluded that Seyfert galaxies accounted for 25% of that. This is a picture of a galaxy, Seyfert galaxy, NGC 1097, with an active galactic nuclei with a supermassive black hole in the middle. This is an optical wavelength, this one, with about 100 solar masses. Here's another picture of, this is in X-ray wavelengths when they're looking at an active galactic nuclei here, NGC 4259 or M106. And this is what it looks like. You've got your supermassive black hole spitting out energy here, jets of particles. They're ramming into all the material around the region, which then generates X-rays. And there's these here we've got here. X-rays reveal huge bubbles of heated gas above and below the galactic plane. So that's a view of one of these Seyfert galaxies in X-rays, and that accounts for about 25% of the diffuse X-ray background. So that was Uhuru. The next satellite to be launched was Ariel 5 satellite. It was a joint British and American project. Also got launched from Kenya in 1974, and it did a lot of productive science for 6 years. The bottom line here, I've just listed all these instruments here, but you don't need to take in all the detail. The bottom line is you can see they're starting to have more instruments and more advanced instruments. They had, for example, the modulation collimator, which gave them that, it was an instrument that allowed them to get more accurate source locations down to 2 arc minutes of the actual source of an X-ray. So versus saying, look, it's over there somewhere, they're able to get more pinpoint. Look, it's more specifically, it's there. They had a high resolution proportional counter spectrograph. In other words, they could really break down into the numbers of X-rays of smaller and smaller amounts of range of X-ray energy levels. They could detect if there was polarization going on, which of course is important for if you're trying to study synchrotron radiation. They also had the scintillation telescope, which was a much more fine, more sensitive telescope. It could help them identify sort of more variations of X-ray fluctuations, and it could handle, quite happily, look up to bright sources up to 40 kiloelectron volts. And they had 2 instruments on board also that could do sky surveys. So you get the gist of it. There's more instruments going up with them and more sophisticated instruments. So what are some of the highlights of Ariel 5? It was able to detect some very sort of fast, sort of short-lived transient X-ray bursts from outside the galaxy. In particular, some cataclysmic variables in Seyfert galaxies. We've talked about Seyfert galaxies already. So how about cataclysmic variables that was able to pick? That was just recapping from a talk 2 or 3 months ago we did. This is where you get another close binary system with a white dwarf here, which is a low mass star which shedded its outer layers, and it's just exposed hot dense cores here. It gets itself close to a red giant or red supergiant. The material siphons off, forms itself into a hot accretion disk, and starts accumulating on the surface of the white dwarf up to a critical temperature and pressure, and then you get a sudden release of energy and you start getting X-ray emissions. So it was able to pick up these, in particular, that these things are quite fast and transient X-ray bursts, and you could identify them from outside our galaxy, from sources outside our galaxy. So it was able to do that. It picked up some X-ray fluctuations called X1 in the constellation of Hercules. Up till now, they knew this whole accretion disk process formed, but they didn't understand it to a great depth. Here they analysed the X-rays and they concluded, yes, we have a neutron star binary system here. And they worked out that these fluctuations of X-rays likely were from changes in the flow pattern in the material in the inner part of the disks, in these inner regions rather of the accretion disks. So that took another step forward in understanding the physics of actually what's going on, the more detailed physics of what's going on in these accretion disks in these binary systems with neutron stars. So every time they looked at something new in some more detail, or something old in more detail, they were able to make more discoveries about these high energy processes going on. They looked at some of the hot emitting gases in the Perseus cluster, as we've mentioned. They did, the Oriole 5 satellite had instruments whereby it could do a closer spectral analysis, in other words, determine what sort of elements in the hot gases were giving out this high energy, and they concluded there was ionized state of iron in the Perseus galaxy cluster that got up to temperatures up to about 100 million degrees. And the interesting thing there is that the presence of iron, the fact that they could do spectral analysis, and they said, hey, there's iron, ionized iron in these hot gases, that immediately told you that the gas between the galaxies in these galactic medium in these galaxy clusters was not primordial. It wasn't just from the original hydrogen and helium from the Big Bang. It was actually iron, which means it was from stellar processes inside stars, inside galaxies that had been ejected out of the galaxies into the intergalactic medial space. So that tells you immediately, how the gases get there as well. Then there's the small astronomical satellite 3, another NASA satellite launched also from Kenya, 1975. Once again, the same theme, improvements in the instruments. They, as you can see here, a lot of X-ray sources are variable, they fluctuate off and on and so on. And so they said, we need to get a better idea of the timing and how quickly and the variations of these fluctuations. And they were able to get timers up there accurate to 1 part in 10 billion. They also had more effective spin stabilizers and control systems, and that enabled them to locate sources with more accuracy where in the sky these X-ray sources were coming from. There was 4 experiments, and they were able to do continuous, precise observations for up to 55 kilo electron volts range at any location throughout the year. Any location in the sky throughout the year, they could continuously watch something and observe it. And that was a huge plus. So if there was a pattern going on, they could pick it up with the SAS-3. Just some of its highlights. They knew about quasars by now. Quasars are like similar in principle to your CFIT galaxies in that they're agalactic nuclei, except they're far, far more distant into the earlier universe, and they're far, far more powerful. So instead of seeing a background lit up galaxy with background radiation and a really strong center, all you see with quasars is one just almighty burning center that's so, so powerful. It outshines its entire galaxy by far, and it's very, very far back into the earlier universe, much, much closer. So they'd already identified quasars, but this was the SA-3 identified the first quasar initially by X-ray and actually discovered, look, there's a quasar, a new quasar we've discovered, why we've picked up the X-ray emissions. They were also able to observe X-ray stellar flares from other stars. So up till now, they'd only been able to study solar flares. They could now start to identify stellar flares from other stars. Further highlights, they were able to look back at the Milky Way galactic center. They noticed these in blue here, all these little X-ray sources. So they noticed there was a lot of little intermittent bursts of X-ray emission around the center. They were able to record those, note their exact position, their spectra, what sort of elements were involved, their temporal variation, in other words, the pattern of how quickly they turned off and on and so on. So that was all much new detail to work out what process occur in the center of the Milky Way. They did a complete sky survey with soft X-rays of the entire sky with unprecedented angular resolution and accuracy. And of course, every time you do a more accurate survey, it puts down groundwork for further X-ray studies. You do that survey and you say, look, oh, these are new interesting little things. We didn't know about these. You label them and you design an instrument in the next generation of satellites to go looking further into those sources. So it's a very important function of these X-ray satellites. NASA then took a step further and they started a program called the High Energy Astronomical Observatory. There's 3 of them dedicated to looking at high energy process, cosmic rays, gamma rays, and X-rays. There was 2 of them, HEA 1 and 2, that were designed specifically or predominantly for X-ray emission. And look at the size of this. Here's a technician here. Look at the size of this, the HEA 1 instrument. So this is in NASA 1977 to 1979. So 2 to 3 years. That was 2.5 by 2.5 meter and weighed 3,000 kilograms. So once again, a huge step forward in the ability. Never mind these, what was the first one? I think in the 60s was 1 by 1, the Geiger counter, 1 by 1 centimeter. Then it went to 100, then it went to 824 by 824 centimeters. We got the satellite has got a 1 square millimeter array of proportional counters. So it was able to catalogue and identify multiple energy sort of X-ray sources, much many sources of fainter magnitude, and of course much more of them. So that's all I'm going to talk about the HEA-1, because the HEA-2 was far more interesting. It was actually, once it got into orbit, they renamed it the Einstein Observatory. And that flew from 1978 to 1991. And the significance of the Einstein Observatory, it was the first proper, fully imaging X-ray telescope. Up till now, really all they had was these sort of detectors getting more and more sophisticated and bigger and more sensitive, pointing into the sky. But they thought, if we get a telescope, the purpose of a telescope is to capture more photons and focus them down specifically onto your detectors. So capture and focus as many photons as you can, and in this context, X-ray photons. Now, so how are you going to do that? Because as I mentioned earlier on, you get a plain plain mirror rather, and a plain detector sometimes. Your X-ray just sails straight through it. It's so highly energetic. So the key to capturing X-ray photons, highly energetic ones, is you've got to have your mirrors at an angle. And there was a Dutch guy, Walter, who first designed some X-ray telescopes many years ago. And they started looking at particularly the type 1 optical design, and it was ideal for X-ray telescopes. And the idea here is you have a twin set of mirrors at glancing angles. This is not to scale, because I put this here, drew this one up because it just illustrates it more easier. But the idea is the X-rays come in at a glancing angle here, and get reflected off the first mirror, which is at a paraboloid configuration, hits a mirror in a hyperboloid configuration, and then gets focused down to the focal point there. So it's 2 mirrors almost parallel to the incoming X-rays, hits them so the X-rays hit it at grazing angles, and that enables you to then capture and focus these high energy photons without them just plowing straight through the mirror. So it was a whole new technology. And it was this guy here, Leon van Spiebroek, a Dutch guy, and he joined Giacconi and Rossi and helped them design. And this guy was considered the premier X-ray telescope mirror designer, responsible for developing the Einstein telescope, and also he went on to design the Chandra X-ray telescope mirror systems. And they were all based on this Walter Type 1. Where now the other thing is, as I showed you previously, you get these. You've got to have the mirrors at a sort of very narrow angle, glancing angle here. Now, which means you probably think to yourself, we can only capture, you can't capture many photons doing that. So how they got around that, to increase the surface area, they put concentric, what they call nests or layers of pairs, of mirror pairs, long like that. So suddenly, even though you're catching these X-rays that are coming at glancing angles, you're actually increasing your surface area, and you are able to capture more over a bigger space. And that was the key to this. So Leon van Spierbroek is really considered the fourth great pioneer in X-ray astronomy. This just gives you an idea of the Einstein Observatory. You don't need to take all this in. The bottom messages here. Look how everything's getting more and more sophisticated, more instruments, more high-powered, more sophisticated instruments, improved resolution, improved sensitivity. And the sensitivity of the Einstein telescope was 100 times more precise than any of the previous missions that preceded it. So this was in itself a huge milestone in X-ray astronomy. So some of its highlights, it was able to study X-ray emissions from 143 stars of different evolutionary states. And what they found was these stars were emitting much more in X-ray wavelengths than the standard models of stellar evolution suggested. Which once again, that helped them refine the models of stellar evolution. We've got to have another think, and because we've got other observations that don't match the model. So it helped refine the models of stellar evolution. What they also discovered in that same process, that when you look at entire galaxies, when you see a lot of the background diffuse X-ray emission going on, that actually stars emitted and contributed much more to that X-ray background emission than they originally thought so. It was also able to study in a lot of depth supernova remnants. It was able to take some spectral observations, in other words, find out what sort of elements were going on inside supernova remnants. That helped to improve the models of nuclear synthesis, in other words, the creation of new elements inside massive stars and the supernova explosions themselves. Furthermore, they were able to map out the surface brightness or the internal structure of you see these big supernova explosions. Inside there's a lot of shock waves going on, and they were able to map out the surface brightness of these X-ray shock waves throughout the various supernova. And this is one of Kepler's supernova. And it goes back to that picture I showed you right at the start of the talk. And if you suddenly study these and map out these contours, you can see that the structure of these supernova explosions is actually quite complex. This was all first done with the Einstein Observatory. So chapter 4, the 1980s, the bottom line here, look, advancements just continued and continued. Interestingly enough, of the 1980s, NASA was conspicuous by their absence. They had no new programs going on. So it was pretty much dominated by the Europeans and the Japanese. The Europeans in particular had Exostat, which worked for 4 years from 83 to 86. And the Japanese had 3 missions throughout the 1970s going, each one of increasing number of instruments and the sizes of the instruments and more sensitivity and resolution and so on. So the developments then continued into the 1990s, where there was numerous, by the Europeans and NASA, launched numerous more and more advanced X-ray observatories in the 1990s. But there's 2 in particular that I want to pull out and talk about, because these 2, the Chandra X-ray Observatory by NASA and the XMM Newton Observatory by the European Space Agency, over 20 years later, are still producing very good science today in X-ray astronomy. So let's just have a brief highlight, have a look here. So that's the Chandra X-ray Observatory, launched by the space station, the space shuttle rather, in July 1999. So that's 21 years ago. Its design here, once again, the Walter Type 1 optical design, and like the Einstein telescope, it had 4 sets of concentrically nested mirror pairs. And that's this is actually a scale diagram of what it was look like. You can see the long focal length that it has there. The other thing is, as I've mentioned in here too, is it was a whole technology to actually capture these high energy photons. And the other thing about these X-ray photons, remember, they've got very, very small wavelengths. So you've got to be very precise the way you capture them and direct them. You can't have rough surfaces. So the surfaces essentially had to be precision polished. They were made of in particular, a substance called Zerodur, which is renowned to be very thermally stable. It was 2 centimeters thick of the Zerodur, this very thermally stable mirrors, and it was coated with iridium. So they went to all that effort to produce these really high precision mirrors that could handle these really short wavelength, high energy X-ray photons with precision. And the Chandra X-ray Observatory, high resolution of your 0.5 arc seconds over a field of view of about 30 arc minutes. So that's a wide field of view and a very high resolution. So that was once again another huge, big historical milestone for X-ray astronomy. Some of its highlights, some of its more recent highlights I picked on here. Within about, I think in the last 2 years, they are able to pick up a new signals, X-ray signals coming from known neutron star mergers, where two neutron stars merged together. They were picked up by gravitational waves, but they were able to use the Chandra telescope and look at this process going on, and the X-ray signals they got matched perfectly the signature for a newly formed magnetar neutron star. A magnetar is a young neutron star that's highly magnetized, rapidly rotating very, very quickly. And they predicted this would happen. They predicted if it did happen, you'd have a certain X-ray emission. And they picked up this merger was going on with the gravitational waves, swung the Chandra telescope around, looked at it, and yep, suddenly they found, look, we've got another signal to say this neutron star merger is occurring, you know, as opposed to just the gravitational waves. We've got another tool that allows you to give you more insight to the process, what's going on when two neutron stars merge. So that was very fortuitous. Another interesting recent finding from the X-ray telescope observatory that they're able to do is, you're probably aware of measuring distances and expansion rate of the universe by type 1a supernova. These bright objects, these supernova explosions, type 1a, very, very bright, occur in distant galaxies. You know how bright they are. They should be by the physics going on. You see how bright they are from Earth. You get the difference between the two, and you can work out the distance. Well, it so happens that quasars, these really highly energetic, highly luminous galaxies, way back in the early galaxies, they soon found out that these emit X-ray radiation as well as ultraviolet. And there was a correlation between the proportion of ultraviolet and X-ray radiation that correlated perfectly with the luminosity, how bright these things are. So they're able to work to observe how bright a particular quasar is, study it in ultraviolet and X-ray, and the Chandra X-ray observatory was used to get the brightness and the amount of X-ray radiation. They could suddenly work out its luminosity, what it should be, look at what a luminosity it is through your telescope, and hey, suddenly you got yourself a new standard candle that you can start measuring distances to galaxies in the early universe, much more powerful than your type 1a supernovas. So that's something new that the Chandra X-ray Observatory is starting to get into. And of course, the results that are starting to come through, that the quasars are also showing that, yes, that the universe is expanding, and it has, the rate appears to be changing over time, has varied. So that's a whole new field of cosmology that they're starting to use the Chandra X-ray Observatory for. So how about the XMM Newton Observatory, launched by the Europeans in December 1999? And here's this, it's actually 3 telescopes in one. So they've got 3 of these Walter type 1a telescopes rolled up, or sort of all assembled into one satellite. And here's something else very interesting, is the nested mirrors. Instead of having 4, which is the Einstein telescope and the Chandra X-ray Observatory, it's got 58 gold-plated nested mirror pairs. So 58. So that's huge increase in your surface area and hence your resolution. And you've actually got 3 of them up here in the one observatory. That's what it looks like there. The collecting area, yeah, how's this for collecting size? 4,650 square centimetres. That's at 1.5 kiloelectron volts. And getting up to harder X-rays, you're getting up to, at 8 kiloelectron volts, you're getting up to 1,800 square centimetres. So you can tell, you know, they're getting more and more powerful, better resolution. So how about some recent highlights from the XMM Newton Observatory that's been up for 20 years, still producing good science. Recently, I think this has all been within the last year or so, they've been able to map the dynamic behavior of matter and radiation, being very dynamic in how it interacts surrounding a black hole. So they've identified a stellar black hole, but they've been able to study through X-ray wavelengths the behavior and interactions of matter and radiation going around that. Once again, that helps to understand the physical, high-energy physical processes going on around black holes and their accretion disks. Also recently, the Newton Observatory discovered hot gases in the Milky Way halo that are up to about 10 million degrees. So that tells us there's a lot of highly energetic gas in the Milky Way halo that they didn't realise what was there. That's been discovered by the XMM Newton Observatory. So chapter 6, yeah, just let's summarise things here, but let's talk about roughly the pioneers, some of the historical X-ray observatories of those crucial 2 decades, the 60s and 70s, and then we'll recap the milestone X-ray discoveries during that period. So these these are 2 of you guys here, pioneers of X-ray astronomy. Herbert Friedman, he was the guy from 1949 using World War II rockets, captured V2 rockets, discovered the X-rays from the sun, worked out what was happening in the ionosphere, but he was hamstrung with low quality detectors and so on. But they concluded from his experiments that it wasn't worth looking much further. And then there was Bruno Rossi, very insightful Italian-American experimental physicist, who said, yep, I reckon soft X-rays will be visible up there. No one would believe him. If you want to know what that quote is, I don't know if anyone can write in there if they know what song that's from. I think it's a cool phrase, born on the breeze and die on the wind. These guys are giants. Friedman was considered the grandfather of X-ray astronomy, and Bruno Rossi considered one of the fathers, along with Giacconi, which we'll look at. It was an Elton John song from Yellow Brick Road. The song has no title. And here, these guys here, and one also considered the father of X-ray astronomy, Riccardo Giacconi. He teamed up and developed new sensors and detectors with Bruno Rossi, and the 2 of them went ahead and pretty much all those ones that I talked about in the 60s and most in the 70s, these 2 guys were behind most of these missions. And of course, the 4th pioneer, recognised pioneer of X-ray astronomy was Leon van Spaebroek. And he was considered, in quote unquote, from one of his obituaries, the premier X-ray telescope mirror designer. And that's another Elton John lyric from Empty Garden. These guys were just irreplaceable. These guys were giant, all guys. So how about the X-ray observatories? The main ones were the 1962 sounding rocket launched in New Mexico. That was the first one that went up, and it showed the whole world, yep, there's the galaxy, the universe is just full of X-ray radiation that we can detect. There's a background diffuse level, and there's some nice little peak sources of intense sources out there as well. The 1970s came along. They got satellites that could stay up in orbit and keep looking at things for longer periods of time. And there was those 5 main satellites, all by NASA. Some of the milestone X-ray discoveries during these first crucial decades. As I mentioned, the 1962 sounding rocket that was initially launched. Yes, it was visible cosmic X-rays, galvanized the whole community, and as I've mentioned, they're the diffuse background emission and powerful point sources. And in the 1970 satellites, they then showed evidence for white dwarf, neutron star, and black hole binary systems, in particular close binary systems with red giants and supergiants that created those accretion disks that then spat out X-ray radiation as material from the accretion disk, fell on to the compact, dense, relevant stellar corpse. They picked up that there was hot gases in the intergalactic space within clusters, which added strength to the idea that there is hidden dark matter out there we can't see, but it's there. They were able to work out that the origin of that background diffuse X-ray radiation is most likely dominated by quasars and the distant powerful quasars in the distant early universe, and more recent times the active galactic nuclei of those Seyfert galaxies. They precisely catalogued many X-ray sources right across the sky for future generations of telescopes to study. And they were able to look at supernova remnant structures and what sort of elements were being formed inside these supernova explosions from massive stars. So here's your homework. Yeah, pick one of these two telescopes, the Chandra or the XMM Newton X-ray observatories. Maybe follow them on social media or something. These telescopes are over 20 years old, with the original technology that was developed by those four great guys, and they're still producing good data and making discoveries today. Pick one of the two of them and follow them on multimedia, or just do some Googling and stuff and have a look at they've all got their own home pages, these observatories, and check out some of the modern stuff that they're still doing. So I hope you've enjoyed it, watching. Thank you for watching Cosmic X-ray Astronomy, and I hope you've seen now some of the historic milestones through these first crucial decades of the 1960s and 70s. You've seen the pioneers, the missions and the discoveries that then everything was built up onto and led to the modern observatories. If you would like to have some more detail, I just scratched the surface of the topic here this evening. I did the sort of a few pages of an article thingy on this, about a 30-page thingy. If you would like a copy of that as a PDF file, you're welcome to email me just at membership@astronomy.org.nz, and I can file you back the PDF. And it covers what I've talked about tonight, but much more detail. So I just throw that out there if you're interested. Otherwise, it covers most of this evening. I think time's up. And Steve, any questions?
Thanks very much for that, Chris. That was super interesting. We have got a couple of questions, but I'm going to start off with one from me, actually. Given that the Chandra and the Newton telescopes are 20 years old, they've been up there. There was some failures on Chandra a couple of years ago. How long do we think these telescopes are going to last, and what's next?
Yeah, good question. How long are they going to keep going? These telescopes were only, their missions were only planned to last somewhere between 5 and 10 years. And I think they far exceeded their expectations. And of course, they can't service them or anything. So they've just done the distance. I think just solid, well-built telescopes. And how long, I don't know how long they're going to go for. They weren't expected to go this far, but they are. So look, they could surprise us and just keep going for many more years. There are newer telescopes, that more sophisticated telescopes that have come out throughout the 2000s. You look on the internet stuff, there's nice little timelines and stuff. So there's new ones being developed all the time, more instruments, higher resolution, and so on. And the reason I showcased those two is because I picked on those two because they have been going for 20 years and they were designed and built by those original pioneers, still had their fingers in those pies. As you saw, sadly, all of those four pioneers have now sadly passed away, but that's the legacy. Their legacy is in those two telescopes. Yet they are getting old, and they have been superseded by newer stuff. But that does not stop them from still producing their own research, new discoveries in their own right. So I can't give you any exact figures, but I hope that answers it to a degree.
Yeah, thanks for that. We've got a question from Dan, sort of related to that, who says, "Great talk, Chris. But how do they decommission these satellites?"
Yeah, a lot of them, their orbits slowly decay, they run out of fuel, and I know obviously these two, presumably they'll be like the rest of them, most of them just re-enter the atmosphere and burn up into the atmosphere. And I know NASA can control that if they see, if they can see that something is running low on fuel, its days are numbered, they will then actually, they'll knock it off. They'll direct it into the Earth's atmosphere and it burns up. These things, I was saying, oh, look at the size of this, they're getting bigger and bigger. But in the big picture, they're not the size of the space station or anything like that. They still are in the big picture, not large. They direct them into the atmosphere. And I know all the ones from the 70s with my reading, and the ones from some of the 80s that are no longer up there. Yep, they've just burned up in the atmosphere. Usually ran out of fuel or something like that. NASA sees it, the writing on the wall, and controls them down into a burn, so they burn up above a large ocean or something like that. But they're not recovered and they're not sent deeper into space.
Thanks for that, Chris. And final question, unless anybody's got any more who want to get in quick, is from a user called Cicada, who says the first X-ray telescope diagram, which was the paired shallow angle mirrors, showed 2 focal points, and this user says, is the data combined from these somehow?
No, it's just one focal point. The other focal point was of the parabolic one, as opposed to the hyperbolic. They are brought to one focal point. They all come down to one focal point. I know the slide you're looking at. It was the not to scale one that I just knocked up myself to illustrate. I think it was this one here he's looking at, and they're all So it's coming down from the hyperboloid is the mirror, they use that focal point there. So it's this is your paraboloid going out here, design here, and that's your focal point, but they're using this focal point here. So that explains it. And the reason I did that, because otherwise you look at here and it looks all of it, you start getting into, you start looking diagrams, scaled diagrams, and it all gets a bit crazy. So I just put the 2 focal points, but they're all brought to the one focal point, and that's where the detectors are placed, and that's where they get the data from. Just one focal point and focal plane.
Yeah, that makes sense. The other focal point is where it would be if the hyperboloid mirrors weren't there.
Yes. Yeah. Correct. Yeah. Correct. Yeah.
Well, that's it for the questions. So thanks again for another really interesting talk, Chris. I know you've been super busy, so it's great that you can take time out on a Monday to teach us things that we don't know. So yeah, just like to say on behalf of everybody, thanks again, and I hope everybody has a great week.
Thank you very much. Thanks, Steve, and everyone be safe. Cheers.
Thanks.
Thank you. Are we